So welcome to Math341 probability. So this is lecture 10. And so what I want to do today is I want to do Buffon's needle in honor of the fact that Pi Day is coming upon us very quickly, and the Crackerjack box problem. So I'm not quite sure if that's enough material. It's a little interesting moving from doing 15-minute classes to our 15-minute classes. So I'll also do a very quick Simpson's paradox. Since we're in spring training right now, one of the more entertaining variants of this is in terms of baseball batting averages. And so that's a nice little problem to throw in. So the big idea is linearity of expectation. It is fine to solve problems by brute force computations. The most important thing is to know that you have a way to get to the solution. But once you have that, is there a good way to get to the solution? Is there a way that is less likely to lead to an algebraic mistake? Is there a way that's more likely to be illuminating, to maybe show what's really going on? And I really want to drive home the power of linearity of expectation. And we've got to be careful which things are linear, which things are not. So the sum, the expected value of a sum is the sum of the expected values. That's true. They don't need to be independent. But it's not true if we look at variances. For there, we do need independence, we need covariances. It's not a prerequisite, but out of curiosity, how many of you have done covariances? Okay, not as many. How many of you have done variances? All right, so a little bit of difference. Okay. So has anybody heard of Buffon's needle? So this is a wonderful problem. So the great mathematician Erdős once remarked, you do not need to believe in God, but you do need to believe in the book. And so according to him, there is this book that has the best way to solve problems. And the highest compliment you can give someone is, that's a proof worthy of the book. For some things, there are so many good ways to solve them, like the proof that there's infinitely many primes. There's multiple entries in the book on it. And so what I'll do today is I'm going to do the brute force approach to Buffon's needle. And then I will show you the book approach to Buffon's needle, which bypasses all the tedious calculations, which is one of the themes of this course. How do you look at things the right way? And so, not surprisingly, because of how influential Erdős was in mathematics, does anybody know what the Kevin Bacon number is? How many numbers away are you? Have you been in a movie with somebody who's been in a movie, et cetera, et cetera, et cetera, with Kevin Bacon? In mathematics, we have Paul Erdős. He wrote over 1,000 papers, I think over 500 co-authors. Then there's the Erdős-Bacon number. And there's a couple of very interesting people who have finite Erdős-Bacon numbers. Big Bang has one, Wonder Years has one. My number is not so great. I have to go through one of the former prime ministers of Canada to get a finite Erdős-Bacon number. But a couple of mathematicians actually wrote a book called Proofs from the Book, where they tried to collect some of the best ways of looking at things. So if you're thinking of doing a math colloquium at some point, this is a great source to get some problems to do. So the way Buffon's needle problem works is, imagine we have a floor with parallel strips of wood, and so we have a bunch of lines. And we want to know, if we toss a rod of a given length, what's the probability it intersects one of these vertical lines? Or if we toss a large number of rods, how many times do we expect to have intersections? So whenever you have a problem like this, you always want to get a sense of what do things depend on. So we've got a couple of natural objects. We have the length of the rods. We have the width of the separation. Do you think the answer depends on the length of the rods? So what should happen is the length of the rod goes up. Intersects more. What should happen if the width between the vertical lines increases? What should happen? Intersects. What should happen if we double the length of the rod and double the separation between the vertical strips? What should happen? It should remain the same. It's just like changing units. So without doing any calculation, the answer should be a function of either L over T or T over L. Doesn't really matter which way you do it. But before doing any calculation, dimensional analysis, I know it's got to be like that. We will assume for simplicity that the rod length is not too large. Why? Well, if the rod length is extremely large, you could have multiple intersections. If the rod length is small, I can have at most one intersection. So let's say the rod length is at most equal to t. How many intersections could I have? I could have one. What else could I have? There's two other numbers. I could have one. What else could I have? 0. And what else? Yeah, if I happen to land perfectly along the line, I would have infinitely many. And actually, there's one more. So it's perfectly parallel to the line, and on the line, I have infinitely many. What's the other possibility? Perpendicular, and I would get exactly 2. In any probability model we do, the probability that it's perfectly vertical or perfectly perpendicular is 0. So I'm not going to worry about that. So I really only have to worry, does the rod intersect 0 times or 1 time? And as long as the rod length is at most the separation between the vertical lines, I'm only going to have 0 or 1 intersection. I can't have 2 plus, or I can't have 3. Okay? So we have to figure out what is the probability density function for this problem. So we are throwing a rod at an infinite grid, at an infinite floor. How many variables do you think we have? Is this a one-dimensional problem, two-dimensional problem, three-dimensional problem? Two-dimensional. So I have to choose a coordinate system, and I have to choose a probability distribution. So I could do maybe the x coordinate of where it lands and the y coordinate of where it lands. Yes.
We don't care about the y coordinate, but we do care about.
Good. We don't care about the y coordinate because I can shift it up or down without loss of generality. So for simplicity, what is the y coordinate when it lands? 0. So really, when the rod lands, instead of doing x and y, and I've got to be careful because I also care about the angle at which it lands. So a huge part is trying to figure out what's a good coordinate system. Let's do the center of the rod and ask, where does the center land? And now I would just care about the x value, and I would care about the angle. And so we just have to decide, how do we want to do things? So here we have lines like this, and we'll do L for the separation. And so here is 0, 0. Without loss of generality, do you agree that we can assume the rod lands somewhere between 0 and L over 2? So again, we're throwing the rods on the board. We're trying to see how often does a rod of length R hit our grid. And we just said it doesn't really matter the vertical component. We might as well adjust so that the vertical component is 0. All that matters is the horizontal. Can I assume the horizontal is somewhere between 0 and halfway? Or do I have to go from 0 all the way up to, oh, I guess they're using L for the length of the rod and T for thickness. Do I have to go all the way up to T, or is it enough to just go halfway? What do you think? Is it enough to go halfway? If I go beyond halfway, can I just flip things? So by symmetry, I might as well just flip things and say, I land somewhere between 0 and T over 2. It's like tic-tac-toe. If I go over here in the upper right, it's really the same as any of these other ones, right? All of these moves are the same opening move. I can't tell the difference. So why not make my life simpler and assume that the initial rod lands somewhere between 0 and T over 2. So without loss of generality, x coordinate of rod center is between 0 and t over 2, what kind of random variable is going to represent the x coordinate? Uniform. So we would say x is uniform 0 t over 2. All right. Now that the rod has landed, let's say the rod lands here. And so it's L halves over here, L halves over here. What's the other variable I need? I'm going to need this angle. What can I assume about the angle? Without loss of generality, angle is between 0 and how far? Pi. So pi seems safe. You know, if I've landed at 0, I can go all the way up to pi. And notice if I go all the way to pi, I've gone all the way around. Do I have to go as far as pi? So there's enough to go to just because if I sat here, if I go to pi over 2, if I go over here, do I really need to do that? Or is that the same as reflecting it about the x-axis? It's the same as reflecting it about the x-axis. So again, you don't have to do these symmetries, but it makes it a little bit easier when you're doing the integration to take into account some of the symmetries. So let's just quickly recap, for those coming in. We are throwing rods of a fixed length L on a grid of vertical lines, and we're trying to see how often do they intersect. The separation between the vertical lines is t. We're going to assume the rod length is at most t, so it can really only hit 0 or 1 vertical line. Without loss of generality, it doesn't really matter the vertical component of where the rod lands. So we might as well assume that the vertical component is 0. It's a two-dimensional problem. We're going to do it based on where is the center of the rod landing. The center without loss of generality is somewhere between 0 and t over 2. Because if it's more than halfway, we can just flip it and use symmetry. We can assume the angle is somewhere between 0 and 90 or pi halves, because we can always flip it about the x-axis. And so what kind of random variable is theta going to be? Also uniform, and 0 to pi over 2. So we have to figure out how many intersections do we have. If I tell you where the rod center is and what the angle is, can you tell me if it intersects? All right, we have to do trigonometry. Okay. So let's try to figure out what the trigonometry is. So here is 0, here is t over 2, here is the x-coordinate, right? Here's the vertical line. And then we've got some angle theta. And so by symmetry, it would be the angle theta down there. So how can we tell if it hits? Any thoughts? Can you give me an angle where it's not going to hit? Pi over 2. So clearly, if it's vertical, it's not going to hit. Can you give me an angle where it hits? 0. So we know it hits at 0. It doesn't hit at pi over 2. And so it's going to keep hitting until a certain point. What's the point when it just barely hits? So it keeps hitting until we have a right triangle with hypotenuse of length L over 2. So keep hitting till have a right triangle of hypotenuse length L over 2. Okay, so we want to keep doing this then until we get to that critical value. So in that critical value, it's going to look like this. So this is going to be L over 2. This is going to be X. And this will be theta. What relationship do we have that connects them? I'm sorry? Yeah. Okay, so give it to me. X over L over 2 or 2x over L. So theta equals the arc cosine of 2x over L. So that's not a bad condition. Okay. I saved myself only one page to do the integration. So we have the integral, x goes from 0 to t over 2, right? And then the integral theta goes from 0 to arc cosine 2x over L. And now we have to integrate the probability. Well, we have two uniform random variables. What's the density of the first uniform random variable? It's a uniform random variable from 0 to t halves. So the area has to equal 1. What should the density be for x between 0 and t halves? 2 over t. It's got to be just 1 over t halves, which is just 2 over t. And for the other one, it's a uniform from 0 to pi halves. So the density is 1 over pi halves, which is 2 over pi. So the joint density is going to be 4 over pi t. Right? So we get 1 over 4, I'm sorry, 4 over pi t d theta dx. Does this look like a bad integrand? The integrand, is the integrand nice? What's the integrand? Yeah, the integrand is 4 over pi t. Does that depend on theta? No. Does it depend on x? No. Is the integrand nice? Yes, right? I can't be much nicer to you. I'm giving you a constant. The integrand is really nice. What about the region of integration? Yeah, there's a reason this is a 300 level class, right? You've got to integrate from 0 to the arc cosine, and then you have to integrate that. X goes from 0 to t over 2. Right? So is the theta integration easy? Sure. So I can pull out the constant. It's 4 over pi t. And now I integrate. X goes from 0 to t halves. And when I integrate, since it's a constant, I just get the length of the interval, which is arc cosine of 2x over L minus 0. So I now have the arc cosine of 2x over L dx. My first thought is to change variables. Right? Let's let u equal 2x over L. So du is 2 over L dx, or dx equals L over 2 du. And x going from 0 to t halves means u goes from 0 to t halves becomes t over L, I think. So our answer is going to be 4 over pi t integral u goes from 0 to t over L arc cosine of u dx becomes L over 2 du. So this is the same as 2 over pi L over t integral u goes from 0 to t over L arc cosine of u du. Okay. You've all passed Calc 2. Can you handle that integral? All right, how?
1 over 1 plus x squared.
Are you sure?
1 over negative squared.
Are you sure?
It's like 50.
So what would you do in the 21st century? Look it up, right? You plug this in somewhere. Or you would try to do some nice change of variable. The first question is, does the answer look reasonable? Well, it only depends on L over T. And we noticed from the very beginning that the answer should only depend on the ratio of L over T. So this is a good sign. Only depends on ratio of L over T. So this is not proof that we haven't made a mistake, but it's not a bad start. One possibility is to do maybe a change of variable. Any thoughts about what might be a good change of variable for you? So can you think of a, yeah. Yes, now you're, of course, you're speaking like a professional mathematician by saying u equals cosine of u. And that's what a professional mathematician would do. But since we are still undergraduates, don't say u equals cosine of u, you should say u equals cosine w, right? You know, just so it's clear that we're not saying u equals cosine. I mean, we are doing that. This is the abuse of notation. Everybody does. But it's better to just use a new letter. Let's try u equals cosine of w. Then du, what's the derivative of cosine? Minus sine of w dw. And then u goes from 0 to t over L implies w. So when u is 0, what does w equal? Pi halves? Right? Cosine of pi halves is, so, and then when u equals t, I'm sorry, when u equals t over L, what does w equal? Arc cosine of t over L, I think. I don't think you can do better than that, right? When u equals t over L, what w corresponds to that? The arc cosine of t over L. All right, notice how I'm writing all the details down. All right, I'm not going to do this, you know, for the rest of the semester, but every now and then it's nice to just go through slowly, show everything. Whenever you're doing multiple change of variables, it is so easy to make a mistake. This is why I always find it's best, write down what the change of variable is, write down how the bounds change. And so now we get 2 over pi, L over t. Now we have the integral, w goes from arc cosine of t over L to pi halves. And now arc cosine of u, we have the arc cosine of the cosine of w, that becomes? Oh, sorry, it is the other way. Thank you. Yes. So it's going to be pi halves. I mean, I really want to put in a minus sign because I hate having the larger one on the bottom. All right, so what's the arc cosine of the cosine of W? W. So I have W sine W dW. And I've got a minus sign. So what does the minus sign do? It goes out or flips the order of integration, which is what I was doing. So using the minus sign, we now go back to where we were. And so now we do have the pi halves up top. We have the arc cosine of T over L down below. Can you do this integration? What do you think? What technique? Integrate by parts. Do we want to use U and dV for my letters? No, because we already have a U in the problem. So I'm running out of pages here. So let's get one more page. I don't squish things. Okay. So we have integral All right. So let's let A equal W, and then maybe dB equals sine of W dW. Then dA would be dW, and B, what's do I get when I integrate sine? It's going to be minus cosine. Yes? And so this should be AB at the endpoints minus the integral of BdA. So it should equal 2 over pi L over T. And now we have AB at the endpoints. All right. We have a minus sign, which is going to flip the order of the endpoints. So we will have W cosine W, flipping them. I think now pi halves goes down on the bottom, and arc cosine of T over L goes on top. And then the minus and the minus becomes a plus, and then we integrate from arc cosine of T over L to pi halves. And then we have cosine W dW. Is that right? All right, so I wouldn't be surprised if I've made a mistake somewhere. So we'll have 2 over pi L over T. When we put in pi halves, we're going to get 0 from the cosine. So we're going to get arc cosine T over L times cosine of W. So the cosine of the arc cosine of T over L, that should just be T over L. Plus, when we integrate cosine, what do we get when we integrate cosine? We get sine. So we get sine of W at the endpoints. At pi halves and arc cosine of T over L. So it's 2 over pi L over T. And if we've done this right, it's T over L arc cosine of T over L. I'm not comfortable that I haven't made an algebra mistake somewhere. The sine of pi halves is 0. So now we have the sine of the arc cosine of T over L. All right, let's try to figure that out. So if I want an angle whose cosine is T over L, did I make a mistake? Oh, sorry, the sine of pi halves is 1, thank you. Plus 1, right? Sorry, thank you. And then minus Now I want the sine of the arc cosine of t over L. Well, if I want something to have a cosine of t over L, if I set it up like that, would this be right? I'm a little worried here. I'm wondering right now if we've made a mistake somewhere, because t is the thickness. And the length of the rod is supposed to be less than the thickness. So if the thickness is greater than the length of the rod, I'm asking for something that has a cosine of greater than 1. So did we make an algebra mistake that nobody noticed? So u, I want it to be 2x over L. So when x was t halves, u should be t over L. Are you looking at this one over here now? Okay, because so when u is 0, oh, did we make a mistake here? What angle? Okay, good. So what angle has a cosine of 0? No, that's going to be pi over 2. Yep. Yep. No, and so the question is, we're integrating up to t over L. So did we make a mistake in the beginning when we have x goes from 0 to t halves? So let's double check. So t halves is the thickness. We want L to be less than t because we don't want it to be hitting too many times. And so the maximum angle is when the hypotenuse is L over t. And so if x is the angle, so the cosine of theta would be x over L halves or 2x over L. Okay, so 2x over L definitely seems right. And so we want u to be 2x over L. So du is going to be 2 over L dx when x is t halves. Oh. Aha. What happens if x is t halves? So if x equals t halves, if you look back to the picture, so if you land right in the middle and the rod is less than L, is there any way the rod could hit? No. So the problem is when we're doing this integration, did we set up the bounds correctly? It is so easy to have the wrong bounds in integration. Remember, when we're drawing the picture, it's important that x can't be too large, because if x is really large, then that's going to have a problem because L over 2 has to be at most x, or right? I'm sorry, it has to be at least x, right? So we missed the following. We missed that x has to be less than or equal to L over 2. So if x is very close to the midpoint, is there any way we're going to have any intersections? Right, so the question is, instead of integrating all the way up to t over 2, what should we be integrating up to? L over 2. Right? Because if x is larger than L over 2, there's no way we can have an intersection. So this is wrong. So these should be L over 2. So we have to go through and we would have to fix that. All right, once we fix that, what else changes? Then this becomes an L over 2. And then what does u go up to? It goes up to 1 now, right? And so now this t over L becomes a 1. Yes? This becomes a 1, I think. All right, that's making things a lot nicer, right? And so now u goes from 0 to 1. And now instead of arc cosine of t over L, what do we get? What angle has a cosine of 1? 0. Isn't that much nicer now? So this now becomes a 0. All right, this is getting much better, right? This becomes a 0. This becomes a 0. This becomes a 0. And now instead of arc cosine of t over L, what do we get? This whole term is just now 0. And then the other one, we're going to get the sine of pi halves minus the sine of 0. What do we get? Just 1. And so we get, if we've done everything correctly, 2 over pi L over t. All right? And we get that the answer is a nice rational multiple of the reciprocal of pi. And the rational multiple is going to be a function of just the ratio of the length and the separation. I love this problem. I'm going to try doing this with 4th and 5th graders tomorrow, not with calculus, just with throwing things up in the air. When I was an undergraduate at Yale, I was president of the math club, and I convinced my probability teacher to give a talk to the math club. And I said, we'll provide the pizza, we'll do all the cleanup. All you have to do is give the talk. He goes, all I have to do is give the talk, you'll do the cleanup, yes. So he talked about Buffon's needle, and he took a box of spaghetti and he threw it up in the air. So now, I was told I don't have to do the cleanup. Let's see if it works as well with wet, sticky spaghetti. And he actually was able to throw spaghetti and get it to stick on the ceiling. Yeah, I had to take my hats off to him. Right? This is a great problem. Somebody used this to try to experimentally measure pi, and they got pi to 8 decimal digits. What someone noticed is, gee, it's amazing that the number of times you threw it happens to be exactly the denominator needed in a great rational approximation to pi. And if you were to throw it one more time, no matter whether or not it hits or misses, your accuracy would drop to 3 digits. It's almost as if you knew what a good rational approximation was to pi and just made up the numbers. But you can't do this experiment. We do have the classroom here. If people want to do this at one point, let me know and I'll bring in some rods and we can throw it in and see how often they land. Okay? So great result. Pi Day is coming. Good to see this. It shows you how easy it is to make a mistake when we're setting up the bounds of integration to say, this all seems reasonable. This is all logical. I'm drawing my pictures. Everything looks right. The problem is, where are things defined? And things are sometimes not defined everywhere, or they're not given the same definition everywhere. It's these piecewise definitions. This is the definition. This is the joint PDF, but only in this region. Once X is too close to the center, there's no way there can be an intersection. Okay, I just did record it, so you had mentioned the antiderivative of arc cosine. So it does involve a square root of 1 minus x squared. There's ways to prove what the antiderivative of arc cosine is. We did the antiderivative of arc tangent. You can play those games. I like playing those games. I'm a mathematician. But 21st century, go through something like this. The other thing is, I strongly urge you, switch the order of integration. A huge part of Calc 3 is doing multiple integrals. You really only know two techniques in multivariable calculus: change variables and switch the order of integration. Is anybody thrilled about seeing integrals involving arc cosine? Okay. If you are, you're either a professional mathematician in training or you need help. Either way, I'm here for you, okay? But most of us are not thrilled when we see integrals involving arc cosine. Well, we have a double integral. Plot the region and then switch the order of integration. So I will leave that as an exercise to you. This is a good way to review your multivariable calculus. Plot the region. And if you have trouble plotting the region because you haven't memorized the plot of arc cosine, what can you do? Go to Mathematica. Have Mathematica plot it for you so you have the shape, and then try to switch the order of integration. Okay. Any questions on Buffon's needle? Yes.
Because you always there's oh two. You also multiply by 2, in which like count both sides.
The 2 just came from just from the length. The length was like L over 2 because we have just half the rod below, and we're only looking at that half which is intersecting. We're not done. The rod can only hit 0 or 1 times. So we're trying to calculate what's the probability it hits exactly once. That's the advantage of having a rod length that's smaller than the thickness. If the rod length was, say, 15,000, then we could actually cross multiple lines. And the idea, linearity of expectation, chop up your rod into lots of little independent pieces, so each one of them is less, and then just somehow combine them. Now, I mentioned proofs from the book. And so here is the proof from the book. Instead of throwing 1 rod, could I throw 4 rods at 4 different angles? And then if I threw the same rod at every possible angle, would you agree that that's kind of equivalent to integrating over all the angles? So I don't want to go through all the details. I'm going to just draw a picture and let you think about this. What's the most perfect shape you can think of? Circle. So we have a separation of length t. What should we take for the diameter of our circle? T. So you take a circle of diameter t, and you try to draw it well. And then if I rotate, if I translate the circle a little bit, again, horrible drawing, but it doesn't really matter. How many times is the circle going to hit the vertical lines? Always 2. If I push it, if it's perfectly centered between them, it hits at the extremes. Otherwise, it's going to hit 2 other places. So there's always going to be 2 hits. And so what's the perimeter? It's going to be 2 pi t over 2. And this should give you 2 intersections. And so I'm not going to go through the details. It's in the proof by the book. But you can see now where the 2 pi is coming from. This is perfectly positioned, so I'm going to have exactly 2 intersections. But you can view the circle as a collection of rods at all the different angles. And then as I throw them down, it's kind of like covering everything. So the proof from the book goes through this very, very nicely. This is hopefully enough for you to see it's not so surprising that a 2π emerges. Okay. So I want to just quickly talk about Simpson's paradox. How many of you have seen Simpson's paradox in the stats class? All right, so this is great. So Derek Jeter in 1995 batted .250, and a year later he improved to .314. David Justice batted .253 in 1995 and .321 in 1996. So in each year, who was the better hitter? Justice. So if you had to choose, who would you rather have on your team? Justice, right? If you only care about offensive production, Justice is the better hitter. But interestingly, over the 2 years, Derek Jeter's batting average was .310, and Justice's was .270. My first question is, are those reasonable numbers? Are you shocked that Jeter's average is .310? Does it pass the smell test? What can you tell me his average must be between? 250 and 314. You know, if you get a 50 on the first exam and a 75 on the second, you're not getting a 95. Right? Your answer should be somewhere between those numbers. These numbers are in the ranges, but amazingly, Jeter has the better batting average over the 2 years. How is this possible? Yeah, so he had a lot more at-bats in the second year, and Justice had a lot more at-bats in the first year. So when you actually look at the numbers, Jeter had 630 at-bats in 96 and only 48 in 95. Whereas Justice had 411 at-bats in 95 and 551 in 96. So Justice, had a lot of at-bats in both of them, but he had so many at-bats in the first year that it really brought down his average. So this is a strange situation where in each year, Justice is better, but over the 2 years, Jeter is better because you have more observations, more data points in the second year. So this is just a fun thing to be aware of. I've put a link to the Wikipedia page. They do also stuff like this with admissions to graduate schools, with medical treatments. I urge you to look at this, that we can present information in a way that seems strange. It seems weird that Jeter could be the better hitter, given that he lost in each year. But it's how much did he lose by? And how much was he competing? Okay. So I want to end with the Crackerjack problem. Has anybody ever had Crackerjack? So you get a toy inside, they're guaranteed. Right? So let's imagine there are capital T toys, and you want to have one of each toy. And we will assume each prize is as likely as any other to be in a box. And all the boxes are independent. I'm not convinced that this is true. I don't know if I sent you this stuff about the Monopoly being rigged. So there are some games where people are a little bit concerned as to whether or not things are truly uniform and fair and whether or not there's some shenanigans going on. We will assume each box is independent of all the others and all toys are equally likely. How many boxes do you expect to open before you see every prize? What can you tell me this should be as a function of T? Should be growing with T, decaying with T. Growing. The more prizes you have, the longer it should take to see everything. Okay, so the first is should increase with T. Let's think of an upper bound. If I think of a specific prize, how long do you think it will take me to get a specific toy? T times. So let's say I give you a specific order. I want to get the first prize, and then once I get the first prize, then I want the second prize, then I want the third prize, then I want the fourth prize. I don't care if I've already seen the second prize. I keep going until I see the first prize. Then I'm happy. I mark down, I've got the first, and then I keep going until I get the second. How long would it take in that case? Get first, get second. How long? Is it 2 to the power T? I don't think it's 2 to the power T. It takes me how long to get to the first prize? T. How long to get to the next prize? T. So now it's 2t.
Oh, it's summation T.
It's summation t, right? So it should be 2t. Have I proven that this is an upper bound? No. But I'm pretty confident. Yes? Oh, sorry, not 2t, sorry. It's t squared, sorry. So t squared, this is not a proof that it's an upper bound, but I'm pretty confident that this is an upper bound. Because this is in the special case of I have to get the first prize, then the second prize, then the third prize. Okay. Can somebody give me a lower bound? Good. And why is that a lower bound? Right, if I want t prizes, I can't do it in less than t. So the answer is somewhere between t and t squared. So I expect to wait between t and t squared. Okay. No, I'm not going to ask you if you enjoyed the integration from earlier today. I'm hoping you didn't. Okay, I'm hoping you didn't like that. I'm hoping you did not enjoy that we made a mistake and we had to fix this. I'm hoping that you're seeing that while we can do a problem with brute force computation, this may not be a good way to do it. But I'm afraid I might not have driven that point home yet. So let me make absolutely sure that you understand that you do not want to do these calculations. If there are any entities you pray to, please pray to them now to make sure we don't make an algebraic mistake. How the hell do we calculate how long we have to wait? Any thoughts? So imagine the teeth prize is obtained at the nth box. Okay. What must be true beforehand? So we have at least one of each of the other t-1 prizes. So we could let, without loss of generality, we have maybe prizes 1, 2, ... t-1. We could let x1 equal number of prize 1, ... x t-1 equal number of prize t-1. We want x1 plus x t-1 equals what? So if we're getting the teeth prize in box n equals n minus 1, and each xi has to be greater than or equal to 1. So if we let xi equal yi plus 1, we get y1 plus yt-1 equals n minus 1 minus t-1, where yi is greater than or equal to 0. But then we have to worry about multinomial coefficients. Because it matters where, we have to worry about how many different ways can we arrange them. We're not saying we have all copies of the first prize and then all copies of the second prize and all copies of the third prize, right? The cookie problem is the first set goes to the first person, the second set goes to the second person, and so on and so on and so on. So I see a relation to the cookie problem, but I also have to worry about how many ways can I reorder. So do you feel like there's got to be a multinomial coefficient coming into play that we have to worry about ordering? It's not enough to just know how many times where I have the first prize, second prize, third prize, I need to look at all possible strings. If I have the first prize 5 times and the second prize 3 times, it could be first, 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 second, 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 or first, second, first, second. So I have to do reorderings. Okay. This should be enough to make you realize we do not want to do this. Anybody know what might be a useful technique that I've said multiple times I really, really like? I'm sorry? Well, simulation would be a good way to estimate the answer, but what is the technique I've said I like?
Symmetry.
Not symmetry. Linearity of expectation. So it all comes down to, can we find the right random variables? Okay. Let's let x1 equal number of boxes till C first prize. So how many boxes do we have to open before we see a prize? First prize haven't seen. Everybody agree x1 is 1? This is not a hard problem, right? I haven't seen any prizes. I open a box. Oh, look, it's a prize I haven't seen. x2 is going to be the number of boxes till C the next new prize. So if you think about it, we can keep going, and xk will be number of boxes till C the next new prize have seen k minus 1 prizes so far. And we have to do this until we get to the t, right? Now, let's define x to be x1 plus x2 plus xt. So how long do I have to wait? It's how long I have to wait on average till I get the first prize. And then how long do I have to wait till I get the next new prize? And then how long do I have to wait till I get the next new prize? So what is the expected value of x? The expected value of a sum is the sum of the expected values. Well, we know the first one is 1, so then it's going to just be the expected value of x2 plus the expected value of xt. So all we have to do is figure out how long do I have to wait till I get the next prize. If you do not like the expected value being linear, I encourage you to do this. Or find any other way to do this directly. Try to write down some kind of joint density function. Okay, if you want to show something is good, you want to show good relative to what? Right? If you want to go to a philosophy department, we can talk about absolute evil and good if you want. But in mathematics, I want to talk relative to other techniques. How is this? Factorization is trivial. You give me a number, I just try all the numbers less than it and see if any of them divide. You know, it's impractical. So if I want to try to do something like this, the probability of making a mistake is so high, I am not confident that I can do this. I was actually hoping I would make a mistake when we did Buffon's needle to just really emphasize how bad it is. And I was pretty sure if I don't review the material before class, I'm sure I'll screw up at least one integral somewhere. I was hoping I'd be able to cover, which fortunately we were able to do so. So now we just have to find out how long do we have to wait if we've already seen k minus 1 prizes to see the next one. Oh, well, that's not so bad. So xk is the number of boxes to open to see the next new prize have already seen exactly k minus 1 of t. So when you open the next box, what's the probability the next box is new? So probability next box is new is what? How many prizes are there? There's t. Of those t prizes, how many are new? We've seen k minus 1 prizes. T minus k minus 1. And if you take the special case when k equals 1, you reduce to 100% probability. Okay, that's good. So the probability it takes one box is p sub k. What's the probability it takes two boxes? So if it takes two boxes, what happens on the first box? I don't get something new. That happens with probability 1 minus pk, and then I get something new on the next box. What's the probability it takes three boxes? It's just 1 minus pk squared pk. So this is a geometric random variable, basically. So weighting is a geometric random variable. So the expected value of x, k, is just going to be the sum n goes from 0 to infinity, 1 minus pk to the n times pk, and I multiply by n. So that's how I calculate the expected value. This over here is the probability it takes n boxes, and then that's the value. And so I can pull the pk out, and so this is just the same as, pk times the sum, and goes from 0 to infinity of n 1 minus pk to the n. So we have to figure out what is that sum. Okay, good. So we must find the sum, n goes from 0 to infinity of n times r to the n. Everybody agree that that's what we need to understand? Okay. So we will see how to do this in Thursday's class using something called differentiating identities. The question is, can we do this without differentiating identities? So what do we know? We know the sum, n goes from 0 to infinity of r to the n. That's 1 plus r squared plus r cubed plus dot 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 equals 1 over 1 minus r. What would r times the sum of r to the n goes from 0 to infinity equal? It's just r over 1 minus r. But on the left-hand side, what would we get? And if I did r squared times the sum and goes from 0 to infinity of r to the n, what would I get? It just keeps going up. So it would be r squared plus r cubed plus dot 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 equals r squared 1 over 1 minus r. And so let's do this infinitely often. And let's not worry about convergence. And so if I sum them on the left-hand side, notice I get 1 plus 2r plus 3r squared plus 4r cubed plus dot dot dot. And what do I get when I sum everything on the right-hand side? I get 1 over 1 minus r times 1 plus r squared plus r cubed. What does that equal?
1 over 1 minus r squared.
Yeah, it's 1 over 1 minus r times 1 over 1 minus r. How close is that to the sum we want? What does it differ by? We want the sum of n r to the n. We want 0 plus r plus 2r squared plus 3r cubed plus dot dot dot. We don't have that. We have 1 plus 2r plus 3r squared. How can we get from this to the first line? What do? Not subtract 1. We want r plus 2r squared. We have 1 plus 2r. What should I do to the bottom? Multiply by r. So if we multiply by r, we would then get r plus 2r squared plus 3r cubed is equal to r over 1 minus r squared. We just figured out what the sum was without, we calculated the expected value. We had to be very clever in how to do this, but we got the expected value. So we know, we now have a lemma. The sum, n goes from 0 to infinity of n r to the n is r over 1 minus r squared. So we show that the expected value of x to the k was pk times the sum, n goes from 0 to infinity of, I think, n 1 minus pk to the n. That's what we showed, right? Well, what should we take for r? 1 minus pk. So this is going to just be pk times, so r is 1 minus pk, so 1 minus pk is in the numerator, and the denominator becomes 1 minus pk, well, that's just pk squared. So it's just 1 minus pk over pk. But pk was t minus, I think, k minus 1 over t. So 1 minus pk over pk. Oh, so much fun, right? Well, you can write pk as 1 minus k minus 1 over t. So the 1 minus pk is just k minus 1 over t. So do we agree the numerator is just k minus 1 over t? Sorry. Yes? All right, so we get k minus 1 over t. And then the 1 over pk becomes t over t minus k minus 1. If we've done it properly. I think I've made a small algebra mistake somewhere. Just quickly double check. So if we've seen exactly k minus 1 of them, then the probability that the next box is new is we have t minus k minus 1 of them over t. That makes sense. You know, when k equals 1, everything works. When we've seen t minus 1, then we get the probability is 1 over t. So that seems reasonable. And then the sum is going from 0 to infinity. in terms of how long we have to wait. Let's think, wait a minute. So we're starting with n equals 0. Is it reasonable to start with n equals 0? That's the mistake. For the first, when there's one box, do we agree that it's never going to be a weight of 0 boxes to see something new? The smallest n can be is 1. So we should really be summing from 1 to infinity. And this should be n minus 1. Right? So really what it should be is, if it's n minus 1, we're going to be pulling out an extra 1 minus p. So it should be pk over 1 minus pk, and then a sum, n goes from 1 to infinity, of n times 1 minus pk to the n. Can I extend that sum down to 0? Does it change the sum if I include the 0 term? No, because I have n times. So this is then the same. So can extend to n equals 0. So there's an extra factor of 1 minus pk in the denominator that we missed. Okay, that's not that big of a deal. So all the analysis here was fine. And then the only difference here is we actually forgot that we have a 1 minus pk down below. Well, that's actually useful for us, right? Because it makes things a lot easier. It makes that a 1. So now we get the expected value of xk is going to just be 1 over pk, which is going to be t over t minus k minus 1. So the expected value of x is just going to be 1 plus t over t minus, we did k equals 1, now we have k equals 2, so it's going to be t minus 1 plus t over t minus 3 plus t over t minus 4, all the way up to t over 1. How can I rewrite the 1? I can write this as t over t minus 0. This is the same as t times 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over t. And that's approximately t natural log of t. This is the harmonic sum. So hopefully you've seen that in calculus, that 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, all the way up to 1 over t is about log t. And so this tells us that the total wait time, the number of boxes, is t log t, greater than t, less than t squared. So this shows you the power of linearity of expectations. I did not mean to make the mistake of dropping the index over here, but it's good to just highlight how easy it is to make those small little mistakes. All right, so this is a good place to stop. Have a good rest of the day.